So today I'm going to talk to you about future projections of regional climate, water supply, snowpack, and drought. Just a minute. There we go. So before I start, I just want to give a little bit of an overview of what we'll be talking about. So overall, we're talking about climate change in the Mountain West. So what are climate models going to tell us about what future climate looks like from a sense of basic climate parameters, and then how that might play out in aspects of water supply, snow, and drought. To summarize what I'll be talking about, in the Mountain West, and by the Mountain West, I'm specifically looking at projections for Colorado, Utah, and Wyoming. We will see increasing temperatures. There will be some change in annual precipitation, but even more importantly, we're going to see there's projected to be a change in the seasonality of precipitation. We will see an increase in potential evapotranspiration. So how the atmosphere is going to impact transpiration of water by plants and evaporation of water from soils. How those three factors, temperature, precipitation, and potential evapotranspiration, will impact runoff. In general, in this region, we'll see less snow and more rain. And we will also see there are projections to be an increase in the regional extent and severity of drought. So I want to first start with looking at the basic climate parameters, really what we need to talk about first before talking about water supply or drought. And that starts with temperatures. This figure here shows climate projections for Colorado, Utah, and Wyoming through the 21st century. This is data that comes from the MACA downscale climate data set and is the average of 20 different global climate models. The red line represents a high emissions scenario, or RCP 8.5. The blue line represents a moderate emissions scenario, or RCP 4.5. And the shaded area represents the uncertainty between those models. So what's the error and standard deviation between those 20 models? And under a high emissions scenario, by the end of the century, we're projected to see an average temperature increase of 10 degrees Fahrenheit. On a moderate emissions scenario, we're projected to see a temperature increase of about 5 degrees Fahrenheit. In general, we'll see the strongest regional warming in summer and fall. And that's something that Becky showed us there with fall and spring temperatures, that there was a really strong recent trend in warmer falls. And there's a lower relative temperature increase in winter compared to other seasons. I do want to just make one comment about the different emission scenarios. When I talk about precipitation, I'm just going to be showing RCP 8.5, in part because there's not a huge difference in precipitation projections. But I also want to make the point that right now, we're in this part of the curve where the high emission scenario and the moderate emission scenario look very similar. Over the next 20 years, what we do as a planet in terms of emissions is going to impact what emission scenario we're on. And if there aren't changes from our current emissions patterns, then we're more likely to proceed on that higher emission scenario. So the next several slides show maps of projected changes in precipitation, and all of these follow the same format. This is data that's from the Climate Explorer, which was a tool that Lenica showed, and the maps are showing percent change in precipitation, the historical period from 1975 to 2005, compared to a 30-year period centered around 2080. And the greener shades are showing increases in precipitation. The brown shades are showing decreases in precipitation. This figure here shows change in annual precipitation. So we can actually see that much of the region is projected to see a slight increase in precipitation on the order of a few percent to 10% increase in precipitation, particularly over Wyoming, the northern 2/3 of Utah, and northwestern Colorado. Eastern Colorado and southern Colorado and parts of southern Utah are projected to see a decrease in precipitation. The next four graphs, I want to dive into the seasonality of precipitation, because when thinking about snowpack, runoff, and drought, the timing of that precipitation and what that precipitation type might be is very important. So this figure, again, it shows all of the same data, but now we're just looking at winter. So this is December through February precipitation, historical period compared to 2080. And for all of the region, there is a significant increase projected in precipitation. And in much of the region, there's a 30 to 40% wintertime precipitation increase. But if you notice where this is located, a lot of these areas with the strongest precipitation changes are at lower elevations. So we have the West Desert of Utah, the Eastern Plains of Colorado, and much of Eastern and Central Wyoming. The smallest increases in precipitation that are projected are in Western Wyoming, much of the Rocky Mountains in Colorado, and Eastern and Northeastern Utah. When we go to looking at projected changes in spring precipitation, we see a much different pattern, and there's a north to south gradient, where in the spring, areas in Wyoming, northern Utah, and northern Colorado are projected to see slight to moderate increases in precipitation, with areas in Wyoming seeing 20% increase in precipitation. However, areas around the Four Corners and in southern Utah and southern Colorado, especially southwestern Utah, will see projected decreases in precipitation. And in southwestern Utah, these may be on the order of 20 to 30% decrease in spring precipitation. When we move on to summer precipitation, we see a regional pattern and another gradient, but rather than moving north to south, this is kind of an east to west gradient. We see significant decreases in precipitation projected in much of Wyoming and eastern and central Colorado, where in much of Utah, we see a slight increase in precipitation. I do want to point out that these increases that are projected in summer precipitation in Utah, they're based on percentages. So we're looking at 0 to 10% increase in precipitation. And many areas in Utah, especially those in western and northern Utah, not impacted by the North American monsoon, these precipitation is very low, on the order of tenths of an inch to an inch and a half per month. So the absolute change in precipitation here for the summer is not very great. And finally, moving on to the fall, we don't see any of these regional gradients. It's a pretty uniform pattern of a general decrease in fall precipitation, with some isolated areas where there's projected to be a slight increase in fall precipitation. So before I start talking about the water cycle and water supply, the final bit of climate projection information I wanted to talk about is potential evapotranspiration. So there is a projected increase in projected evapotranspiration through the end of the century. Potential evapotranspiration is essentially a measure of the atmosphere's thirst for water. So what I mean by that is the temperature and conditions such as humidity, wind speed, radiation that cause transpiration from plants, or that drive transpiration from plants and drive evaporation of moisture from soils. These data here come from 20 climate models downscaled from the MACA climate data set, and is for a single location in Utah, West Jordan, Utah, which is near Salt Lake City at about 4,300 feet. So a relatively low elevation site. The left panel here shows the moderate emissions scenario with the red circles, and the right panel shows the high emissions scenario with the blue triangles. And this is looking at just absolute increase in potential evapotranspiration through 3 time periods. By 2060, there's projected to be a 5 to 8% increase in potential evapotranspiration. 5% for the moderate emissions scenario, 8% in the high emissions scenario. By 2085, there's a projected 7% increase under moderate emissions scenario in potential evapotranspiration, and a 13% increase in potential evapotranspiration under a high emissions scenario. There is some seasonality to this. Relatively, the highest Potential evapotranspiration increases are projected to occur in winter and spring. Potential evapotranspiration increases in winter probably do not have much of an impact on water supply and, and, and stream flow. However, increases in potential evapotranspiration in spring may have an impact on runoff and municipal water use for outdoor landscapes. And this change in potential evapotranspiration can have a significant impact on water availability, both through the amount of runoff that's available in streams and rivers, and by impacting the amount of water needed for outdoor water use in municipal settings and agricultural settings. So before I talk about specific projections of drought and snow, I want to just talk a little bit about water budget and put some of these changes into kind of real world contexts of water budgets. And Becky kind of touched on sort of this way of thinking about precipitation and temperature and sort of refilling that reservoir of soil moisture. So your basic water budget for a given watershed is you have an input of precipitation and an output of evapotranspiration. So this is evaporation of water from soils and transpiration of water from plants. And precipitation minus evapotranspiration equals runoff in a very simplistic way. So I want to take an example of a watershed in our region, in the upper Dolores River watershed. This is a rough water budget for a normal year. You have an input of 30 inches of precipitation. About 60% of that precipitation is lost to the atmosphere through evapotranspiration on a normal year. It's about 18 inches. So that leaves 12 inches for runoff, or about 40% of that precipitation that fell. And in this case, that 12 inches of runoff equals a normal runoff year, or 100% of runoff. Now, I want to talk about two specific scenarios. One, what happens in a drought scenario, and two, what happens in a climate change scenario to this simplistic way of looking at water budget and runoff. So in a drought year, you're kind of impacted on both sides of the water budget by decreases in precipitation and increases in evapotranspiration. Typically in a drought year, you have increased evapotranspiration for a couple reasons. One, if there's less precipitation, that typically means that you have high pressure, clear skies, greater solar radiation, and often higher temperatures are associated with drought. Potential evapotranspiration is a calculation that uses relative humidity, temperature, wind speed, and solar radiation. So typically on drought years, you have changes in all of those parameters. So let's look at one particular drought year that was an exceptional drought year in southwestern Colorado and much of our region in 2018. In 2018, about half the normal precipitation fell, about 15 inches, and this amounted to 49% of normal precipitation. And there was a significant increase in evapotranspiration. Evapotranspiration took away about 85% of that precipitation was lost to the atmosphere through evaporation and transpiration. That left only a little over 2 inches of that runoff available for stream flow, which amounted to 19% of average stream flow. So what happens thinking in the future in terms of climate change? Well, considering the data we just looked at in terms of precipitation, much of the region, there's a slight increase in precipitation. And for this part of Colorado, southwest Colorado, I think there was a very small increase in precipitation. So we're going to say that precipitation is not going to change in the future. But what we are certain about is that temperatures are going to change. While temperature isn't the only factor calculating potential evapotranspiration, it is a significant factor in calculating that potential evapotranspiration. So if temperatures are increasing, evapotranspiration is going to increase. And another thing that we know from looking at those projections is many regions, especially in around the Four Corners, are projected to see a decrease in spring and summer precipitation. So that means a decrease in cloudiness and an increase in solar radiation, which will likely lead to higher temperatures and again impact and increase potential evapotranspiration. So let's look at how that sort of scenario plays out. And we're going to use some numbers from those potential evapotranspiration projections I showed. So we still have a normal precipitation year. Let's imagine this is the year 2060 or 2080. 30 inches, 100% of normal precipitation. However, potential evapotranspiration has increased. So now we're losing 70% rather than 60% of that precipitation to the atmosphere. So now we're left with only 9 inches for runoff rather than 12 inches. And this amounts to 75% of normal runoff. So this is an example of the kinds of things that could happen in the future when thinking about increases in temperature, increases in potential evapotranspiration, and how that might impact runoff. In this case, and I don't think we should use this as a rule of thumb for everywhere in the region, but in this simplistic case, a 10% increase in evapotranspiration caused a 25% reduction in stream flow. So now I'd like to finish off the presentation with just a little bit of information about projections of snow and drought. This figure here comes from the National Climate Assessment and specifically looking at snow water equivalent in Utah and Colorado. Each of these red bars represents different time periods. And I do want to point out, compared to the other southwestern states, Utah and Colorado have some resilience towards snowpack and snow water equivalent loss. And that's due to the relatively higher elevations of both of these ranges, especially Colorado. By the end of the century, Utah is projected to see about 66% of historical snow water equivalent, and Colorado is projected to see about 74% historical snow water equivalent. Now, I want to talk a little bit about the impact, projected impact of warming on snowfall, on basically whether that snow is going to fall as rain, or that precipitation rather will fall as rain or snow. And this figure here shows the probability of precipitation falling as rain or snow. The blue colors represent 100% probability of rain, and then red moving towards white represents an increasing probability of snow. So I want to point out the shoulder seasons: October, November, March, and April. And you have one column where you have historical probabilities for rain, snow, and another column for mid-century probabilities for rain, snow. And you can see that in these shoulder seasons, there's a large decrease in the probability of precipitation falling as rain and snow throughout much of our region. I also specifically want to point out the very ends of the shoulder seasons, October and April. In October, especially in our region, there is 100% probability of precipitation falling as rain, except for some of the ranges in Wyoming, and a very small chance in Colorado. And in April, there is also a significant reduction in the probability of precip falling as snow. And that's often, for high elevation areas, still a very important month for building that snow water equivalent. And as we've heard about, that later season precipitation can be very important in maintaining later season stream flows. Now, finally, to end with a little discussion about drought, to just review some of the things that we've talked about that will impact drought in the future. We're projected to see increases in temperature, which are going to have a tendency to increase droughtiness. We're seeing many parts of our region a decrease in spring and summer precipitation, and an increase in potential evapotranspiration. All of those factors would tend to tilt the system towards a greater likelihood of drought. And I want to finish with some projections about the geographical extent and the severity of drought projected for by a recent study for 2 regions. The study breaks the country regionally, and we're going to focus in on the southwestern region and the Great Plains region. And this work classified drought through the by using the standard precipitation and evaporation index. And we can see here that the geographical extent of drought is not projected to change during winter, which makes sense based on the projections we saw of precipitation. However, during summer in both regions, especially in the Southwest, there's projected to be a dramatic increase in the geographical extent of drought. And in the Southwest, under a high emission scenario, that approaches 100% of the region. In the Great Plains, there's projected to be a slight increase in the extent of drought in spring and fall. But in the Southwest, Utah, being part of that region, there's projected to be a significant increase in the extent of drought, approaching 50% or above for much of the region. And finally, this shows some projections about the severity, how the severity of drought is projected to change. This is showing the colors are showing the number of years that out of 50 that there's projected to be a moderate or worse drought. So the warmer colors, the darkest color represents 40 out of 50 years that are going to be in moderate or worse drought. And again, this is based on the standard precipitation and evaporation index. You can see there's a pretty small increase in the severity of drought during spring, fall, and winter. With the exception in the late century time period, there is a greater increase under the high emission scenario in the severity of drought. But really what I wanted to focus on is that during summer, there is projected to be a significant increase in the severity of drought moving forward, especially in that late century time period under the high emission scenario, all the way to the right of your screen. There's many areas that 30 and 40 out of those 50 years are projected to be in moderate or worse drought. And with that, I'd be happy to answer any questions.